Welcome back. Today we are going to study selective transmission. So in our unit on waves, we have a quick recap. We did longitudinal sound waves first. We talked about intensity, decibels. We talked about amplitude, loudness, and we talked about wavelength, frequency, and then we moved on to the electromagnetic spectrum, which were unique from longitudinal, at least from sound waves, because they don't need a medium to travel through. In our continuation, we with light waves, we talked about reflection and refraction. When you shined a light, the angle of incidence could refract or reflect. And now we're going to talk about what happens with transmission, and then more specifically, selective transmission. Today, we will focus on some key vocabulary words. We have absorption, when something is absorbed. We have selective transmission, reflective, or reflection, reflect, and we have just transmission. So, I forgot to tell you, I'll give you a few seconds here. Grab a piece of paper. If you have your science notebook, that would be fantastic to keep all of this together. This will definitely come up in your high school physics class. So when you get your paper, you can go ahead and put pause and go grab your paper and come back. You're going to copy the list of words shown below. We have transverse, longitudinal, reflect, absorb, transmit, selective transmission, and light. So for part A, you're going to look for a relationship among the words. What do you notice? What patterns do you see? This is a unit on waves, and everything in here has to do with waves. And one of the clarifying pieces of why the category isn't waves is because waves isn't one of the terms. So if we want to figure out what the overarching category is, we have to figure sort of out like what word includes all of the other words, but what word is left out. So the B is which word should not be there. So we know about transverse waves. We know there's the perpendicular to the energy flow. Longitudinal waves are parallel. We've been studying reflection, absorption, transmit, selective transmission, and light. So if you could pick one of these terms that does not belong here, cross it out, go ahead and do that on your paper. Then you will, for part C, circle the word or phrase that sort of includes all the others. So what is the overarching theme here today? There's definitely some clues for you to use. And go ahead and circle the overarching theme. So this is our theme, and every other term, besides the one I crossed out, is included in that. And then in your notebook, how are the words or phrases you circled related to the other words? So what is the relationship between that main category and the other terms on here? When you're ready to start writing, hit pause and you can fill that out in your student notebook. And when you're ready to keep watching, go ahead and unpause. Here is an example of a sort of best choice scenario for these terms. Longitudinal, those parallel waves, we really haven't been talking about them for a while. I also do want you to notice down on the bottom for activity 11 here. So at the bottom of the screen where it says activity 11, the name of this activity is selective transmission. So there is our overarching theme. And then within selective transmission, we're going to look at the transverse wave, which is a light wave, electromagnetic, got those. And then how does it transmit energy? And what about absorption and reflection? Selective transmission in general is, on the bottom, I sort of summed up what we were combining those words. Selective transmission of light, which is a transverse wave, is when some light is simultaneously reflected, absorbed, and or transmitted through a material. So the idea of selective transmission is the energy from the sun transmits from that sun's surface to the Earth's surface. That is an electromagnetic wave traveling 96 million miles to reach the Earth. When that electromagnetic wave reaches the Earth, some of the energy is absorbed, some of the energy is reflected, and some of the energy is transmitted through. So we're looking at the relationship between all of those. Selective transmission is that relationship. So, what happens on different surfaces? Do different surfaces matter with selective transmission? Obviously, yes. What about surfaces on Earth? And so you are already going, well, wait, hey, I know that the Earth is mostly covered by water, so I wonder what the difference between water and land is. Activity 11, selective transmission, is a laboratory, so we will make do. And much like activity 10, it's really fun, and I wish we could go outside and do this. But alas, we will watch a video and still be together virtually. In previous activities, you saw how waves, such as sound and light, transmit energy from one place to another. Light can be transmitted through one material into another. Any light that is not transmitted through a boundary between two materials is either reflected or absorbed by the object it hits. Like sound waves, light waves are reflected when light bounces off an object, either sent in one direction or scattered in many directions. When we see an object, we are seeing the light it reflects. Light waves are absorbed when light enters an object and does not exit the object again as light. The energy is not gone, but is now in the object. This absorbed light is usually converted into heat that warms up the object. In this activity, you will investigate the transmission, reflection, and absorption of waves from the sun that are not visible to the human eye. Now, think about the waves that are visible to the human eye and think about what you already know about absorption and reflection. So it's super, super, super hot outside, and it's going to be like a 90-degree day, which I looked at your forecast, Denver. Thursday is supposed to be 89. And you know what happens in Denver when it's 89? Y'all are so close to the sun, being a mile high, that if I decide to wear a black shirt out running, I'm going to be running in that 89 degrees sun. And what is that black shirt going to do? It's going to absorb the sun's energy. And when it absorbs the sun's energy, it heats up and gets hot. And when it heats up and gets hot, it feels so uncomfortable. So most of you will choose, especially summer clothes, to buy workout clothes that are light colored, maybe white. So if I'm out in the sun and it's really, really hot and I'm wearing a white shirt, it feels cooler because much of the sun's energy is reflected and not absorbed. So we're going to have a few activities where we talk a little bit about this idea of reflection and absorption, starting with today. So stained glass. Sunlight is selectively transmitted through the stained glass window. Some of the sunlight is absorbed and some is reflected. And I think most of you can predict and anticipate what you knew from elementary school about colors. And so with the visible light spectrum, the reason why chloroplast in plant cells that are doing photosynthesis look green is because those chloroplasts are absorbing the wavelengths of the sun's energy in every single wavelength of visible light except green. Green is the reflected, so that green hits the leaf, bounces back into your eyeball. Lo and behold, you see green. So we know a little bit about reflection and absorption. Let's see what else we want to know. Notice that in this activity, this last sentence here, we are going to investigate the transmission, reflection, absorption of waves from the sun that are not visible to the human eye. So which waves do you know are transmitted from the sun that our human eye cannot detect? Fill in that blank. Which waves from the sun are transmitted that our eyeballs cannot detect as visible light? You got it? We'll come back. So our guiding question today, what part of sunlight is transmitted through selected films? So the experiment that we would do is we would take our phospho boxes again. So those phospho boxes that we used last class where we looked at a little bit of absorption and reflection with the colors and how much energy. We're going to take those same phospho boxes and we're going to open them. And there's the phospho strip on the bottom, but we don't need that right now. Right now, we're going to put a thermometer in each box. And so I have enough boxes for you that in your group of 4, you each get 3 boxes. And in those 3 boxes, the experimental question is going to be the different types of film. So there's this plasticky film that we place on each box, and there's a film A, a film B, and a film C. And if you were to feel them, they sort of have a little bit of different textures, different thicknesses. And so that would be the differences between the 3 films. And then we're wondering, do the films cause the energy from the sun to act differently, to selectively transmit differently? We are going to start with our data in our notebook. So again, if you have your science notebook, awesome. If not, please just get out a piece of paper so you can record some data and be a little active in this activity that's pretty passive. So in your first column, you'll have the 3 different films, A, B, and C. We're going to analyze the initial temperature. So before we go outside, before we do anything, we're going to keep our thermometers. Actually, we are going to go outside and we're going to keep our thermometers in the dark and we're going to let them acclimate to the air temperature. We're going to then record what that air temperature is. Then we're going to put the 3 different films on the boxes and we're going to expose them to sunlight. And I can't remember exactly, maybe 5 minutes, maybe 20 minutes for this. We're going to expose the thermometers, but the difference between the 3 is the exposure is under a different film. Then we're going to record the final temperature. Then we're going to look at how much did that temperature change. So go ahead and pause, write this data table down, make sure you have it ready to go. As we watch this part A of our video, please fill out your data table that you wrote in your notebook.
Selective transmission. Part A, comparing temperatures. Each thermometer was placed in the bottom of the box and a film was secured with tape on the top of each box. Record the initial temperature inside each box. Box with film A.
Oops, let me go back just a tiny bit and pause it for a minute to make sure you see the scale. You know, when I'm looking at a thermometer that I haven't seen, I need to check and make sure what is the scale? What are we counting by? This is degrees Celsius. So I see here is 20. That big number 20 is sitting on this long line. And we know with Celsius especially, and with scales, we really like to count by tens. And so are there 10 lines between 20 and 30? 1, 2, 3, 4, 5. Look at that, the shorter, right? Like that longer but shorter than the big. 6, 7, 8, 9, 10. So sure, each of those bars is 1 degree Celsius. And so if I look at 20, there's 20, there's 25, 26, 27. It's a tiny bit above 27. But in the scheme of things, let's just call it 27. That's film A.
Film A. Box with film B. Box with film C. The boxes were propped in this position, allowing each box to be exposed to sunlight for 5 minutes. Record the final temperature inside each box. Box with film A. Box with film B. Box with film C.
So when we go back to our data table, make sure you had the initial temperatures. And for my data table, I wrote down the initial temperatures were all about 27. They were really darn close. The point ones and point twos are really difficult to see because we didn't have little marks on the scale for us to be more accurate than a whole or maybe a half. I did notice that for box A's final temperature, it was about 42. For box film, B's temperature, it was 34.5. And for C, it was 40.5. And so when I look at the temperature changes, and these all, I mean, the reason why we have initial, final, and change is maybe the initials weren't the same, but in our case, they were. The change in temperature, film A increased, that plus increased by 15 degrees Celsius. Film B increased by 7.5. Film C increased by 13.5. So we're noticing that with the sun's energy hitting the film, some of the sun's energy was selectively transmitted. If the sun's energy wasn't absorbed, it was reflected. So from this data, what do you think was the best film at reflecting? What do you think is the best film at absorbing? And there might be situations in the world where you want to do both of those things. I was messing around with Google Sheets because I think it's fun and I love analyzing data. So I took the data from this data table and I made column A, column B, column C, column D in Google Sheets. And I put in the data and I made a bar graph because it was just really clear and easy to see. I could have done a line graph and saw how things changed, but I thought the bar graph was just more clear. And I see that with film A, and the films really aren't connected. There's 3 different films, so a bar graph does make the most sense. Notice what I did to you to make the data look more significant. Can you tell? The data wasn't that far apart, especially between 15 and 13.5, but I actually manipulated the y-axis so that it looks like a greater difference. Film A started at 27, blue bar, and the final temperature, 42. Film B, film C. So which film absorbed the most? Which film absorbed the least? Which film reflected the most? Which film reflected the least? Those are the questions that you're asking to be interactive in the learning and analyzing this data. As you're analyzing and thinking about the data, why is this even important? And what do we even need to know this for? Okay, that was part A. Part A is done. We have analyzed the temperature in the film. And so when we think about light waves from the sun, we do have visible light. In this experiment, we weren't really measuring visible light because we weren't seeing when we had, and you didn't really get to see this that well in the experiment, but when we had these boxes here out into the sun, you couldn't really see the reflection. You can't really see the absorption. So how do we know it's there? We measure temperature changes. And those temperature changes are the change in energy and will give us an understanding of which of the films selectively transmitted differently or more or less. And that evidence is useful because I can't see that with my naked eye, with my visible light spectrum. For part B, this part gets really fun, and I'm desperately looking for a cool experiment that you can do at home, because a lot of the experiments, especially with UV, they require a UV meter, or there's these little sun beads where you can buy these beads that will change colors in the UV light. So I'm trying to look for something that would be maybe an item you would have at home and could just practice and experiment with. For the temperature one, if I wanted to experiment with temperature in the sun, I could certainly set up different materials to absorb and reflect differently. So I can come up with something for you to do that would be real easy. I don't know if you have thermometers. Uh, and so if you don't worry. If you do, that'd be really cool. Like if you took a black shirt and put a thermometer underneath it and put it out into the sun next to a white shirt with a thermometer underneath that and put that out in the sun, what do you suppose the difference in absorption would be? What do you suppose the difference in reflection would be? So the lab aids, the curriculum that we use, they have these little UV intensity meters that are super cool. They're just wallet-sized cards, like a credit card size. And on the bottom, you can see that there's this white strip that indicates that there's no UV been exposed. It's just the white strip. This strip is it's an indicator, so it will change colors when UV light hits it. And you can see on the bottom, if it's really light purple, the UV the UV meter, it's low. And then we get moderate, high, very high, and extreme. My brain struggles with the low being written in dark color and the moderate being written in dark color and the high being written in light color. So this is really confusing because like I'm really trying to look at the background here and see the changes. Below you can see that there's some SPF ratings, and we'll come to that later. So with the UV intensity, what we're going to do is we're going to, instead of using thermometers, we're going to take the films off, remove the thermometer, and we're going to put the UV card in there. We're going to put the film back on. Now the UV card resets itself when you put it in a dark place. So you put it in your pocket and you wait a little while and it will reset to that white or blank, that 0 UV rating. And then when we expose it to sun, it'll change colors. So we could do one just exposed to sun without any film, and we're definitely going to test the 3 films. So for this experiment, go ahead and pause. And please write down this data table. I suppose you could continue on your film A, B, and C on the site and write initial and final UV. So we're going to look at those cards before we expose them to the sun, and then we're going to look at them after they've been exposed to the sun under the different conditions of the cards. And so our independent variable was the type of film with 3 levels of our IV because we had film A, B, and C. Our control would be a thermometer just out in the sun sitting there. And for UV, just the UV meter. So this experiment will be explained to you here while you're watching. Please fill out your data table.
Activity 11, selective transmission. Part B, comparing ultraviolet. The thermometers were replaced with UV detector cards and the experiment was repeated. Record the initial UV level inside each box.
So this initial level to me was low. It's not super white, but it's not pink or purpley at all. So I went ahead for film A and just put 0 equals low. So in the bottom, you can see there's a range of 0, 2, 5, 7, 10. And I can't see the extreme one over here because it's hidden. But right now, the 0 low is before we've exposed the card to anything.
Box with film A. Box with film B. Box with film C. The boxes were propped in this position, allowing each box to be exposed to sunlight for 5 minutes. Record the final UV level inside each box.
So for this, you're trying to look at the color of the strip. It's also really hard for my brain because the outside frame is purple. So if you were to estimate how much that strip changed from 0 to what, go ahead and do that on your data table.
Box with film A. Box with film B. Box with film C.
All right, back to our data table. How did you fill that out? Here's the data I came up with. For film A, the initial was 0, and that final was about a 6 for me. It was in the high color of that purpley range. For film B, I thought it went 0 to about 1. Pretty small change, so low. And then for C, 0 to about 2. It was a little bit darker, but not much darker for me, and so I still categorize that as low. So now we have a couple of pieces of data and evidence for not only temperature change, but UV. Thinking about what we've collected and what you've seen, was the light that was not transmitted reflected or absorbed? What do you think? Let's look at this question. According to the data that was collected, film A, B, and C, temperature changes in UV, which film transmits the most energy? Why do you say that? That was long and awesome, and I'm super sad that we couldn't do this together, but this is the next best thing. I hope you enjoyed selective transmission, and we'll continue learning more about waves tomorrow. Bye.